Hello everyone. In this video we are going to start with a new chapter on the Föppl-von Kármán plate theory. The plan is exactly like in the development of the theory for beams. So first we had, back when studying beams, we had developed first the theory for the bending of beams, and then we had gone on to study the buckling of beams. In exactly the same fashion, in the previous chapter on the classical plate theory, we had developed our equations and we had studied the bending of beams, the bending of plates. And in this chapter, we're going to develop a theory to study the buckling of plates through this Föppl-von Kármán plate theory. Now, I believe this is the first chapter which is actually named after two scientists, August Föppl and Theodor von Kármán. Okay, so before we proceed, as a mark of respect and as a nice historical recount, let me just briefly mention a couple of things about them. So Theodor von Kármán, this is the same von Kármán which we are all familiar with from our undergraduate studies on fluid mechanics. So probably you remember him from the topic on the momentum integral equation, or perhaps some studies on turbulence. However, Föppl's name may be a little bit new to most of you, but it is very interesting to note that Theodor von Kármán, he did his PhD under Ludwig Prandtl, and this is the same Prandtl we had again studied in our undergraduate days while studying the boundary layer theory. Okay, so many people do not know this, but Ludwig Prandtl in the initial days of his career had actually worked on elasticity problems. In fact, his own PhD thesis was on a problem involving a T-shaped bar, on the tipping problem of a T-shaped bar, where he had considered some issues associated with its elastic equilibrium. And believe it or not, the professor with whom Ludwig Prandtl had done his PhD thesis was none other than Professor August Föppl here. So in this theory, you have actually Theodor von Kármán and his, basically what we can term as his academic grandfather, August Föppl. Okay. So that's very nice. So with this brief historical recount, let us get to the actual business of developing the equations of this Föppl-von Kármán plate theory. It is also important to note that despite this grand history behind it and this great gentlemen who were behind the development of this theory, there are certain issues with this plate theory. Okay, now those issues are rather sophisticated in nature. So to even understand those issues, you need a certain sophistication in both your mathematical and your physical understanding. So at these initial or preliminary days of your studies of plate equations, elasticity, it is probably not right for me to go into those kinds of issues. Rather, let us try to first learn these things, and as your brain matures more and more, you will yourself realize some of the issues that are present. Okay, so for now we just study it very much as part of our syllabus, and please do not get disheartened by the fact that there may be some issues with this theory, because it is also very much true at the same time that this Föppl-von Kármán plate theory has been utilized to a great success in a wide range of very classical engineering topics, in actually building things which are of immense importance, like submarine hulls. You can even read about it in a Wikipedia page. And very recently, like relatively very recently, over the last 10 years, this Föppl-von Kármán plate theory, it has been utilized in a number of very interesting physical problems. So it has its uses. All right, so just like we had done in the case of beams, we are going to first start out with the kinematical hypothesis, and we'll see that as a slight twist on the kinematical hypothesis that we had developed in the context of classical plate theory, what we are going to do here is to consider a little bit of a modification of that. Okay, so what we are going to say first of all is that well, for our kinematical hypothesis, we still have these relations. So you can check the kinematical hypothesis that we had used in our classical plate theory. These are the same equations that we had used back there. Okay, so here this u is the deflection or the displacement variable along the x direction. This by itself is a function of both x and y. This v is the displacement variable along the y direction, and it is also a function of just x and y. I should correct myself. The us itself is a function of both x and y. The vs is a function of both x and y. The u, you can see there is a dependence on z here. The v also does have a dependence on z. Okay, so it's the w which purely does not have any dependence on z. Okay, it's a pure function of x and y. All right, so up to this point it is exactly the same as classical plate theory, but the difference comes now when we consider the strain components. Okay, so just like in beam theory, when we were considering buckling, we had to modify the consideration of the strains by taking the nonlinear terms. In exactly the same fashion here too, we are going to incorporate the nonlinear terms. But before we can do that, we have to note something very, very important, which we had done back in the buckling of beams also. We'll consider that this term, the del w del x, that is going to be significantly larger than both del u del x and del v del x. Furthermore, del w del y, that is going to be larger than del u del y and del v del y. Now it is this place actually where the problems start. The thing is, I mean, what is the justification for this? Why is it appearing? So this is actually, I mean, in a rather funny way, it is attributed to the genius of Theodor von Kármán. It said that like he was a Hungarian genius. He has said that, so it must be true. Whether it is physically motivated or mathematically motivated, what is the magic behind it? Well, let's not get into that, but we recognize the fact that there is an issue with saying things like this. Okay, so it's like this, it kind of works, but and it has been justified to a certain extent, but after a lot of trouble. Okay, I'm digressing. So let me get back to the derivation. So based on this, if we consider the strains, okay, and this will be the nonlinear strains. So the expression, if we refer back to what we had studied in the kinematics chapter of our previous course on applied elasticity, it's this. So this is the general expression, and because we have already said that del w del x is going to be larger than these other two terms, what basically happens is that this expression, it approximately boils down to, and if we just substitute the expression for u also from here, what we obtain is del u is del x minus z del square w del x square plus, so there is no approximation in these first two terms. The approximation is in dropping this one and just writing like this. All right. Next, for EYY, we have del V del Y plus half del U del Y square plus del V del Y square plus del W del Y square. Again, that gives us del V as del Y minus Z del square W del Y square. So we are basically using this expression now, and then we are going to drop this one and this one based on this a priori assumption. So we end up with just this. And please note that this is not really an equal to, rather it's an approximation. Next, for EZZ, we have del W del Z plus half, so this is the general expression, del U del Z whole square plus del V del Z whole square plus del W del Z whole square. And please note that this W is a pure function of x and y, so you don't have, well, this term vanishes and this term vanishes also. So this del U del Z, well, you can see from here that this del U del Z, if you consider this del U as del Z, that is going to give us a 0, because this US is supposed to be a or assumed to be a pure function of x and y. So also this Vs is a pure function of x and y. So what this term, this del U del Z, is going to contribute is just this minus del W del x, but there's a whole square over it. So we are going to end up with half of del W del x square plus half of rho. So from here we use this del V as del Z is 0, and this gives us minus del W del y, and that finally gives us del W del y square. All right. Next, we have for EXY, the general expression is del U del Y plus del V del X plus del U del X del U del Y. So these are the quadratic terms for this shear strain, del Vx del V del X del V del Y plus del W del X del W del Y. All right, so we have to do this a little bit more carefully. The del U del Y, that is going to give us del US del Y minus Z del square W del Y del X. So that is from the expression of U. This V is going to give us del V del Vs del X minus Z del square W del X del Y. But you see, this term and this term is exactly the same, so that can be simplified in the next step. Regarding this term, this del ux del ux and multiplied with del u del x multiplied with del u del y. Well, you see, if you just compare this del u del x with this del w del x, so that part is much smaller than that, and similarly this del u del y is much smaller than del w del y, so this entire term can be neglected compared to this. In a similar fashion, this del v del x is much smaller than del w del x, and at the same time del v del y is much smaller than del w del y, so this product is much smaller than this product. So these term and this term, they are negligible compared to this last term. So what we have here is just this last term, and of course instead of an equal to, we should put this as an approximation. Okay, so now this gets simplified to del us del y plus del vs del x minus twice z del square w del x del y plus del w del x del w del y. Okay, next for eyz we have half del v del z plus del w del y plus del u del y del u del z plus del v del y del v del z plus del w del y del w del z. Now you see, okay, let me just deal with these first two terms. From here I have minus del w del y, and from here it's just what it is. Okay, so this is going to cancel with that, but I have to be a little bit more careful, even more careful now with these terms, because unlike what was happening earlier, I cannot make a direct comparison with as I was doing earlier. Okay, so you can see here I cannot make a direct comparison between this term and this term. Okay, and I cannot directly say that it is just negligible. Okay, I have to do a little bit of more work. Okay, so from here this del u del y, I obtain del us del y minus z del square w del y del x, that is multiplied by and I'm going to simplify here a little bit. So this u, so this is going to give me minus del w del x. Okay, next for this del v del y, I have del vs del y minus z del square w del y square that multiplied by minus del w del y. And finally you note that because w is a pure function of x and y, this del w del z, it is going to contribute to this being 0. Okay, so this cancels with this, that last term is 0. Now what do we do with this? Okay, so here we have to argue. You see, even if we had not substituted this, okay, even if we had not substituted this, this would have been a del u del y. Okay, this would have been a del u del y, and this would have been this del v del y. Okay, probably it would have been simpler to just keep it like that. Now we had earlier said that the del w del x is larger than del u del x as well as del v del x, and del w del y, that is larger than del u del y and del v del y. But I think it would have been better if I had just said that these two terms, this del w del x and the del w del y, they are of the same strength. Okay, so if it is true that del w del y is significantly larger than del u del y and del v del y, it must also be true that del w del x is larger than del u del y. So we can neglect this term compared to this. Similarly, we can neglect these two terms compared to this. Okay, so it is as if that they are of the same kind of strength, and these four terms, they are of the same kind of strength. So whenever we are directly comparing with any one of these with any two of this, it is the left hand side terms which are going to be dominant. Okay, so in that sense, this term is going to dominate over this entire thing. I might as well have not substituted here, that would have been clearer, but anyway, I have written it. This term would be larger than this. Okay, so overall, what we are going to get here is that this is a very small term, this is a very small term, this also is a small term. So if we just check up on the previous page, you will see that we are keeping terms which are of this strength, but suppose if this term or this term were to be multiplied with something small, then it would have been pointless to keep that. Okay, now just maybe pause the video here a little bit and think about it. It's saying something like this, that suppose this entire two terms, it is of strength, let's say 0.1. We keep that. However, if that itself gets multiplied with another term which is let's say which is small, like again 0.1, then the multiplication, the product of that with that would be very small. It would be of 0.01. So in that sense, what we are going to do now is to say that this particular combination, this particular product, that is going to be negligible. Again, this particular product, that is going to be negligible. So overall, what we're going to say is that this is going to be neglected and set to 0. All right. Okay. Now next, we consider the EZX. So we are going to proceed in exactly the same fashion. For EZX, we have half del W del X plus del U del Z plus del U del Z del U del X plus del V del Z del V del X plus del W del Z del W del X. Del W del X remains as it is. For this del U del Z, we end up with minus del W del X, so that cancels with that, and this del U del Z, that gets replaced by minus del W del X, and this del U del X, that is going to give us del US del X minus Z del square W del X square. Next, this del V del Z, that is going to give us minus del W del Y multiplied with del Vs del X minus Z del square w del x del y. And this last term, because we have the presence of this del w del z, that is going to contribute a 0. So exactly following the same kind of arguments that we had made for the EYZ term, we are going to say that this particular product is negligible. Again, this particular product is going to be negligible. So overall, this is 0. All right. Now, what we have finally then is the EXs, which is like this. And please note that here this first term and this last term, they are independent of Z. Similarly, this EYY, here we have this first term and this third term, they are independent of Z, and this EZZ, that is independent of Z. Okay, so can we perhaps write this in a somewhat simpler fashion? So just notationally, what we can do is and this we are going to use throughout. We are going to write our EXX as EXX naught minus Z del square W del x square. Let me write that Z a little bit better. So you see what I have done here is within that EX naught, okay, so you understand that within that EXX naught, I have kept these two terms, del US del X plus half del W del X square. So you can just check here. So this first term and this last term, that I have captured within that EXX naught. In a similar fashion for this one, I'll capture this del Vs del Y plus half del W del Y square within a EYY naught. So EYY, that will be EYY naught minus Z del square W del Y square, where the EYY naught is equal to del Vs del Y plus half del W del Y whole square, and the EXY, let's see what we can do about it. Here, sorry, I've missed this bracket here. This EXY, again this term and this last term, they are independent of Z, and this is not. So what we are going to write this as is EXY naught minus Z del square W del X del Y. And please just note quickly what we have done here is that this half cancels with this 2. So I just have this minus Z del square W del X del Y. And here this EXY naught is equal to del US del Y plus del Vs del X plus del W del X del W del Y with a half in front of everything. All right, so overall, let's see what we have accomplished here. We have written down these terms in a form where the Z dependence has been isolated, but and also this EZX has been set following our assumptions. We have managed to approximate that to be equal to 0. Now, what about these terms? This EZZ, it contains within it the del W del X square and the del W del Y square. So it's something like this, that in this EXX term we have the presence of this, but we do not neglect it. You see, it is very much present in that EXX naught. This term is very much present. Similarly, in the EYY naught, this term is very much present. So we directly cannot say that we are allowed to neglect these sort of terms, okay, for the EZZ. But you note that I have not directly written in this final recount this EZZ. Okay, so what is going on here? Well, you see, the EZZ, that does remain non-zero, but just as in the classical plate theory, where we had forcibly taken the sigma ZZ to be 0, here also we'll do such a thing. So when we finally go on to the application of the virtual work equation as a first step towards the derivation of the governing equations, we are going to set out by saying that the sigma ZZ is going to be equal to 0. And because the sigma ZZ would have gotten multiplied by the EZZ, so even though EZZ by itself is not 0, but the contribution to all the terms, because we assume that sigma ZZ is equal to 0, that doesn't really contribute. Okay, so ultimately what we are going to play around with is this EXX, this EYY, and this EXY. Okay, and the whole game will be around these terms. All right, so this was about the kinematical hypothesis, and as you can see, it is certainly more involved in the classical plate theory and also the corresponding version in the buckling of beams. Okay, on that note, I'll end this video, and in the next one I'll start with the application of the virtual work equation. All right, thank you very much.